Swayam Prabha. Digital India. Educated India.
Jnanam Paramam Dheyam. Knowledge is supreme.
Okay, now I want to recall some facts which we will use in the proofs about field extension. So before that I will just make a couple of definition. So when I have a ring A local, actually the definition will not use localness, but so when I take sing A, this is by definition all those prime ideals P such that A localized at P is not regular. This is not necessarily local. So look at all those prime ideals so that A localized at P is not regular. So this is a subset of the spectrum of A. This is called a singular locus. Of A or of spec of A. And we want to prove that the singular locus is open set or closed set. Okay, so this we want to study this, or we want to give a criterion. How do you decide some prime ideal P belong to the singular locus or not in singular locus? Such a criterion is called a Jacobian criterion, and this is similar to we will attach some matrix to this, and then we will study the rank of that matrix, and the correct rank will say that whether P is singular or not. Okay, so first I want to recall some facts from the field theory. From field theory. Okay. So everybody know what a perfect field is. Perfect, a field is called perfect. One definition is every field extension is separable. Every algebraic field extension is separable. If every algebraic, this is what we will use more often, every algebraic field extension is separable. And what is the field? When do you say field extension is separable? So we have L over K, field extension, algebraic. We will say that an element X in L is separable over K if the minimal polynomial of X over K, it is the smallest degree polynomial in Kx, so that X is 0 of that polynomial. This polynomial is irreducible polynomial. This polynomial should not have multiple roots, repeated roots. This one, if this polynomial has no multiple roots, multiple zeros. That is equivalent also to saying, if you would have seen the discriminant of this polynomial is non-zero. Do you know what is the discriminant of a polynomial in general? So, discriminant of a polynomial is the difference of the roots and then squares and so on. So, I will not go much into this. Okay. Okay. Characteristic 0 fields are perfect. Another thing I will need is, if I have a finitely generated field extension, L over K finitely generated field extension, which is separable, then there exists separating transcendence basis. There exists a separating transcendence basis. You know, finitely generated field extensions have a transcendence basis. So, transcendence basis means the pure part and algebraic part. Now, one wants to find a transcendence basis in such a way that the algebraic part is separable part, and such a transcendence basis is called a separating transcendence basis. Okay. Then, so I think better that I will not state exhaustively, but use it when it comes. Okay. So, now I want to state the Jacobian criterion at least today. So, we have an ideal A, let us say, which is generated by F1 to Fm. This is in a polynomial ring over a field in n variables. Okay. So, and P is the prime ideal, P prime ideal in the polynomial ring. First I will do it for the finite type K algebra, and then we will remove that assumption also. K x1 to xn, which contain A, and I will assume this P may not be minimal over A. So, I will choose a minimal prime which is contained in P. So, A contained in Q, contained in P, this is minimal prime. Minimal prime over A which is contained in P, maybe P itself is minimal prime. Okay. Now, we have these polynomials, m polynomials in n variables. So, as usual, the Jacobian matrix, that is d partial derivative of fi with respect to xj, this. So, you get how many cross how many matrix. So, these are the polynomials now. You get now how are you denoting this m, j is the column index and I is the row index. So, this is m cross n matrix. So, this is actually matrix is m, mn and over the polynomial ring. And of course, I can read this matrix mod this P, the given P is given to us. So, read this matrix mod P, that means we are reading these entries mod P. So, dfi by partial derivative to xj, these I am reading mod the ideal P. So, this way you will get a matrix m cross n again, m, n, k x1 to xn mod P. This is the matrix we obtained. Now, this is like a Jacobian matrix. All right. So, the first assertion is the rank of this matrix. So, the first part of the assertion is rank of this matrix dfi by dhj mod P is less equal to height of Q, where Q is the minimal prime over A which is contained in the given P. Okay. Second assertion is if equality holds here. So, if equality holds in A in 1, then the ring is regular. Which ring? Take k x1 to xn mod that ideal A, and of course, this you have to localize where? You have to localize at P mod A. This ring is regular. So, that means you see now at least this 2 gives you a good criterion, because for finite type K algebras at least a given P, whether the localization is regular or not, you have to compute this matrix and compute its rank, and whether it's equal to the minimal prime which is contained in P, then it is regular. Okay. So, its third statement is if I take the quotient field, if I take, see the only thing we have given is A and P. So, if I go mod P k x1 to xn mod P, then we get a domain, and if you look at the quotient field of this integral domain, if see I want to write the converse of this, I want to write the if and only if condition, and if you notice in 2 we have only one way condition, if this then it is regular. So, in 3 we assume that, so if this quotient field is separable over K is this base field, given base field. See this extension, this field may not be algebraic, this may not be finite. So, if it is separable over K, then the converse of 2 holds. What does that mean? If this ring is regular, then the equality will hold here. So, 3 reads the equality holds here if and only if this extension is separable and the ring is regular. Okay, the separability hypothesis, this separability hypothesis is automatically holds if your base field you are working with, that is perfect, because for a perfect field that is the definition, or also it will hold if this prime ideal P you started with, actually it is a special kind of prime ideal, if it is actually a maximal ideal and if it is actually a point, then it will hold. So, I will just remark it here, I will write it, so it is, the statement will be clear. So, this separability assumption in 3 holds if either K is perfect or a P, the given P is a maximal ideal. P is a prime ideal in K, not only a maximal ideal, it is a point. That means P is generated by elements polynomial x1 minus a1, xn minus an. This is also denoted by m suffix a, where a is the point. Then it holds, because in that case what will it be? The residue class ring will be just K. So then you are saying K is separable over K, that is always true. So now first of all, before I go on, first of all there are several things to check here. One very important is, suppose somebody takes different generating set for the ideal A, then the matrices will be different and the entries will be different and so on. So one should check that this rank of this matrix does not depend on the coordinate that we have chosen, the generating set and then the coordinates. So all these has to be checked. Okay. So this I will do it. So what do I need to do it now? So this is precisely what one means by Jacobian criterion. This theorem which has these three parts, that is called the Jacobian criterion. For regularity. Okay. So let us write some lemmas which we are preparing for this. So lemma, I will need at least two lemmas. So let us write them, number 1 and number 2. So P is a prime ideal in the polynomial ring in n variables of height m. So remember, one of our main concern is we have to relate the rank of the matrix with the height of a prime ideal. Okay, the part 1, there exist m elements f1 to fm in P which generates the localization P k x1 to xn localized at P. Is it clear? That this I can find m polynomials, height m is height, so that the localization in the localization at P, the ideal P will be generated by those m elements. So you see we have a prime ideal in k x1 to xn, P is a prime ideal here, and we are looking at the localized ring, A localized at this A x1 x2 xn localized at P. So I can find elements here f1 to fm, so that if you go the ideal, you push the ideal here, that is generated by those m elements. Okay. And 2, if I look at the quotient field of this mod P, this is separable field extension. If this is separable over K, then the rank is equal to m. then the rank of this Fi's dxj's mod p equal to actually m. Okay, so let's understand this field extension is concerned, right? This x1 to xn mod p. This is an integral domain, and let us call L to be this field extension. This L is the quotient field of this. This is the quotient field of this ring. So therefore, this quotient field is generated over K by the images. The small x1 to xn are the images of capital Xi in this residue class ring. Okay, now what is the dimension of this? We have studied the dimension of this finite type K algebra. So the dimension of K x1 to xn mod p, this dimension will be equal to n minus the height of p. This is if you remember when we did normalization lemma and then several corollaries of that. So this is n minus m. M is the height of that prime ideal we are taking. But we have a normalization lemma, we have proved dimension of this finite type K algebra equal to the transcendent degree. So this is also equal to the transcendent degree of L over K, where L is the quotient field of this, right. This is normalization lemma. This was a consequence of normalization lemma. So this L over K has a transcendent degree n minus m. Let us call n minus m to be K. So K is the dimension of this ring, which is the transcendent degree of L over capital K. So that means there is a transcendence basis which consisting of K elements. So that means we will find L here and L naught here, which is generated over K by, now what do I call it, variables. Let us call it y1 to yk, this, and then this contains k. Now this part is algebraic part and this part is the transcendental part. Yeah, round bracket. Now if this extension was separable, then see that was the assumption in 2 somewhere, this extension is separable, that means this extension is separable. You can assume if this extension is separable, we can choose y1 to yk, so that this extension, this is algebraic extension, not this one, this is separable. That is called a separating transcendence basis, and that one can always do it. That is a theorem in field theory. If you have a separable field extension, then you can always choose a separating transcendence basis. Now we are assuming that. So now we are considering, now what do? We consider, take any L, take, so L naught. Okay, so L, take K x1 to xk and then polynomials after that, xk plus 1 to xk plus L, and you see now these are the I am trying to define a map for each L L is in between 0 to M. Remember the notation K plus M equal to N. M is the height of the given prime ideal, N is the number of variables, and K is the dimension. So, from here to L, what do you do? For this xi, this x1 to xk, you map it to those transcendent separating transcendent basis. So, xi is going to yi's up to k I is from 1 to k. So, next time I will repeat a definition of separable extension in general for arbitrary field extension, and then we will continue this proof.